All right, so I'm tired of job hunting, so it's time to do something fun. So I thought, why not do Conway's Game of Life? And I think I'm going to do it a little different. I think I'm going to do it three ways. The results are going to be the same, but the coding style and the organization is going to be very different. The first one is going to just be straight, super simple in Python, nothing crazy. And the second one, still Python. They're all going to be Python. Then the second one, I'm going to create some classes, add a little bit more code organization, but, again, the same result. And the third, I think that I'm going to push myself a little bit. I'm going to try and make Conway's Game of Life with adaptation, which means that each critter on the board will have an opportunity to evolve a little bit and then share those evolutions with its neighbors. Let's go ahead and get started. So this is my channel's GitHub repo. I will share this in the comment or in the description down below. But if we do a quick ls, we'll see everything that I've done a video on so far. This directory here is something vaguely useful. And since I'm starting yet another new series on this channel, let's go ahead and follow the same pattern that I've established here. Oh. So it looks like I've got day, month, year, the episode number, and a short description of what the code directory contains. So let's go ahead and follow that pattern. And since I'm coding just for fun today, let's create a new directory just for fun. But first, let's check out a new branch. Let's call it just for fun. All right. Now we're going to make a new directory called just for fun, or let's call it JFF, just so that I'm staying consistent with the abbreviation. And let's go ahead and create our episode directory. And while I'm at it, I think I'll go ahead and create the subdirectory for solution one. So we want, let's see, it is 9th of September 2025. It's episode 1 and Conway's Game of Life. And if I'm triggering you with dashes and underscores, the dashes are meant to be informational, and then anything with underscores is meant to be human readable, but I don't want to put spaces in here just because it makes CDing slightly more annoying. So that's why the mixed use here. And then the subdirectory is method 101. All right, so we'll go one directory level higher and we'll fire up VS Code. And then in here, we don't have anything yet, so let's touch our new file, JFF, method1 main.py. And like I said, I'm going to keep this super basic. I'm not even going to create a main method here. So what's the first thing that Conway's Game of Life needs? It needs a field for all the critters to play in, right? So let's just keep it simple, use a list. And we'll call this map or world. Map is a Python method that's built in. It's a type that's built in. So we're going to call our area that our critters live in the world. So world is a list. Now we need to define the size that our list is going to, or it's going to be a two-dimensional array or a two-dimensional list, as Python might call it. So we need to start thinking about what dimensions we want our list to be, our world to be. So I think for columns, I want 80, just because that's a good terminal size. And then rows, what's the default terminal size for rows? 24 rows. So we're going to do 24 by 80. Sounds good to me. So now we need to populate our world, right? So we already have our world as a list, but we need to loop over the number of rows and populate each column. So we're going to start with 4 underscore in range, because we don't really care about the index since we're just going to be appending, or I'm just going to be appending the content. 0 and rows. And then every single time we have a new row, we want a world.append an empty list. All right, and then for every column, we want to populate with a Boolean, true or false, to declare whether or not there's a critter that's alive in that spot in our world. So I'll just do double underscore for lack of something better. Range 0 columns. For now, I'll just put pass here, because why is it? Oh, need the word in. There we go. So now we need to think about a way of setting the density, the chance of whether or not we'll start that point with a critter or not. So for that, I'm going to use the random method. This is where I'm going to jump into Python really quick. I think from random import randint, that worked. Randint, and then we're going to do 0 to 100. That works. And then I want a way to define, say, a 5% chance that'll be true. Randint less than 5. All right. Oh, oops. Less than or equal to 5. Went over too far. All right. And let's say 50, just so that we've got a 50% chance of this statement being true, and we can start validating whether or not my logic is correct here. False, 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 true. Okay, false, true, false, false. All right, okay. You know, maybe we're a little below 50%, but close enough here. So we're going to go ahead and copy this logic over into here. And we are, we need to import it from random import randint. World sub, we always want the last one. So we're going to say -1 to always get the last dot append. And then we're going to effectively append this Boolean. So we've got a good way of initializing our data. Now let's start thinking about a way we can visualize the result. We're going to loop over our rows and columns of our world. So for our in world, and for C is for critter in this case, in R, let's see, let's do an if condition here. Actually, I'm going to do an inline if condition. This is no, I'll keep this simple. Let's not do an inline if condition. Let's go ahead and expressly write this out instead of putting it on a single line. I'll put it on 2. So if C, then we want to print we want to print. Let's print a capital O, and then else, just so that we can see that there is something there, we'll print a period, let's say. No, we shouldn't print it yet. Let's actually build up our string. We'll call this str world, and then str world plus equals our capital O. Then we'll copy and paste this down here and change the O to a period. And at some point we need to add a new line. At the end of every row, let's add a new line. All right, and then if we print str world, we should see our world nicely. Now, out of the gate, I want to be Good about my syntax formatting. Bare minimum, I'd want to make sure that the formatting was good, so I'm going to use the tool black to fix my formatting for me, because I've already mixed my quotes with single and double. So black, main.py, one file reformatted, lovely. I'll go ahead and test it out, make sure everything looks good. Oh, you see, I've got an extra new line in here somewhere that I don't want. That's because I need to unindent this one level. 2 levels? 2 levels. Okay, let's try that again. There we go. That looks a lot better. Is this 5% density? I don't know. Sure, seems about right. All right. Now that we have our world and that it's fully populated, we need to start thinking about the actual logic of Conway's Game of Life. You know what? Let's start by making this its own method. So we're going to first of all move this up to the top, and we are going to say def print world. It's going to take in the world colon, and I'm going to tab that in, and we can test it out by saying print world. That way it's just easier to reuse that code, and we can keep the code a little bit cleaner as we progress along to the next stage of actually implementing the logic for Conway's Game of Life. So save that, let's test it again. Uh-oh, what did I do? Yeah, of course, I need to pass in world. There. All right, there we go. So now let's actually start implementing the logic. We're just gonna put this in infinite loop. So, all true. Oop, Python wants a capital T. And then we're going to do another loop that's very much like the one in print. We want to go over our rows and columns. Get our indentation correct here. All right. Then I'm going to say pass, because it looks like I've got 2 space indents enabled and Python wants 4, so let's fix that with black. Now, the first thing we have to consider is that we can't modify world while we're also evaluating it inside of our loop. So we're going to need a new world that will then get assigned to the world variable. So let's call our new world NWO, New World Order, because it's the order of the new world, right? So NWO equals an empty list. And then the next thing we need to consider is that we're going to need, for every point in the world, we're going to need the neighbor of those points. So let's enumerate our world. So we get the index value of the row. So row index, then the actual row itself. And then we're going to do the same thing for our critters. So column index or critter index in enumerate row. So the first bit of information that we're going to need to be able to evaluate every single point in our world is all the neighbors. So let's define a new method up here, and we'll call it get neighbors. And then we're going to pass in row index, and let's not capitalize it, column index. So let's do some bounds checking. Let's also pass in the size of the world. There's a few ways that I could handle this, but just for the sake of simplicity and legibility, I think passing in the world size is going to be the easiest thing. So world size is going to be, we're going to have it be passed in as a tuple. So we're going to have to remember that going forward. And the 0 index of our tuple will be our number of rows. And the one index of our tuple will be the number of columns. Just for the sake of the way we're talking about this, let's reverse these around. So let's create a new list. We'll call it neighbors. And actually, you know what? Let's not pass in the world size. Let's go ahead and pass in our world. Then we'll establish the size inside of here. And the reason why I want to do that is because I actually want, instead of returning the indices of our neighbors, I actually want to return each neighbor themselves, since it's all going to be passed by reference anyway. So inside of here, let's establish a new variable called row count, and just pronounce it that is 0, and column count. And row count, let's see, that's going to be the length of our world. Our columns will be the length of world sub 0. And of course, this is a little inefficient to be doing this every single time, you know, just keeping this version super simple. All right, and now the next thing that I want to establish is the behavior of the method range. I'm pretty sure I already know what's going to happen, but I want to validate the behavior. So for every single time, for every row index, we want to do -1 and +1, but I think the +1 will only get us the number that we already are. I don't think it'll get us one past that, so I think we'll actually have to do +2, but let's validate that before we move any further. So we'll hop into the Python shell again, and then we'll do, let's say our index is 0, 0, so we'll do range of 0 -1 and 0 +1, and I think what we're going to end up with is -1 and 0. We won't have the neighbor to the right, which will be 1. And let's cast this to a list just so that I can more clearly see that the behavior is what I thought it was, and it is. So we will need to do +2. That way we get the neighbor to the left, we get our own index, not necessarily ourselves, we might be in the row above or the row below, and then the neighbor to the right. All right, we will do for ri in range row index -1, and then row index +2, as we just discovered. And then we're going to do the same thing. Actually going to type it out for ci in range column count -1, oh, minus please, and column count +2. Oh, we don't want column count, we want column index. Now we want to do some bounds checking to make sure that we're staying within the indices of our two-dimensional list. So we want to make sure that we're not less than 0 and we're not greater than our row or column count. If ri is greater than -1 and ci is greater than -1 and ri is less than row count, and oh, no comma, and ci is less than column count, we're going to do neighbors.append, and we're going to do world sub ri ci. Now we can return our neighbors. So let's go ahead and fix our formatting. And we'll hop back into Python, because I'm pretty sure that the way this is developed at the moment, all of this stuff will happen when I import specifically get neighbors, and then we can test get neighbors, because my Python shell should have world populated already. So I'm going to say we're already CD'd into the correct directory. So if I say from main import get neighbors, all right, I printed it out. Oh yes, and now we're stuck in the infinite loop, of course. So let's control C out of that. And then we're going to need a fresh shell because Python will probably cache that. We'll go ahead and comment this out for now. Then we'll do our import again. Excellent. And we should be able to see if world exists. Oh, it does not. Let's instead import main. Okay. We should be able to say main.world. Yes. Excellent. So now we can say main.get get neighbors. And let's start with 0, 0, main.world. All right, and then the upper left-hand corner should have 1, 2, 3. Should only have 3 neighbors, so we failed to exclude ourselves. So let's go ahead and jump out of here. We're going to add one more statement to this if condition. And let's see. Let's compare tuple, and RICI does not equal row index column index. All right, it's a very long if statement. I hate it, but it's all right. And we'll go ahead and reformat because I bet that's going to want a word wrap now. Sure enough, it does. We'll import main. And now, yeah, okay, great. We've got 3. And if we do, let's see, 23, because we have got 24 rows and 80 columns. So if we do 2380, we should get 3 again. We only got 2. Oh, because I want 79. There we go. And let's pick something in the middle that we should get all neighbors. So 5, 5. Got 1, 2, 3, 4, 5, 6, 7, 8. And if we take this dot as an example, we've got 3 above, 3 below. So that's 6, and then 1 on each side, so that's 8. Now that we're successfully getting all of our neighbors, we can, I feel like I've been saying this a lot, but now we can start thinking about the actual logic implementation for Conway's Game of Life. So let's go ahead and get out of here. We'll comment this back in. And then for every row index and column index, we want to get our neighbors. So neighbors equals get neighbors, RICI, and our world. And because all the logic within Conway's Game of Life is dependent on just the number of counts of the neighbors, not where the neighbors are relative to us, just our neighbors themselves, we can just go ahead and reduce our neighbors down into just a sum. So I have an idea how I want to implement this, but let's quickly jump back into Python so I can validate my belief. So I've got 2 thoughts. Let's do the one I'm more convinced will work. So let's just make a list of booleans really quick. True, true, false, true, false. So we've got 3 trues in this list. So we will l.count true. Excellent. That makes it nice and easy. So we're going to create a new variable called living count. That will be neighbors.count cases of true. And just to validate one more time, let's also count our false. That's 2. True, true, false, true, false. Yes, only 2 false. So, perfect. So now let's quickly look up the rules to Conway's Game of Life. And just for reference, we will copy this, paste it into our code. Comment it out. And we'll unindent it. Actually, let's go ahead and make these our comments inside of the loop. So we'll re-indent these, so to speak. Any live cell with fewer than 2 live neighbors dies, British spelling of neighbors, as if by underpopulation. So, if living count, let's rename this. Let's call this neighbor living count. It's a little lengthy, but it's a little bit clearer. Let's be consistent with their spelling. Alright. If living count is less than 2, New World Order sub -1 dot append false. Now, I've missed something here. Every single time that we start looping over a new row in world, we need to append an empty list so that we will always have a -1 inside of New World Order. So, wo.append an empty list. Now this is where the order that we see in Wikipedia can screw us up a little bit, because any live cell with 2 or 3 live neighbors lives on to the next generation, but any live cell with exactly 3 neighbors becomes a live cell. So I think we probably want to do this evaluation first. So let's cut this comment out. We'll paste it in down here. We'll do an elif. Oh, and let's fix our neighbor living count variable here. It's exactly 3. All right, and because the next rule, it doesn't matter if it's living or dead, because we're guaranteed to have a new critter in that location. So we can do NWO -1 dot append true. All right, and any live cell with 2 or 3 live neighbors lives on to the next generation. Now we've already handled 3, so really we only have to handle 2, right? So let's put another elif, and we'll say neighbor living count equal 2, New World Order, -1. We're going to append. We're going to append whatever the value is in the current state of the world. So we'll do world sub row index sub column index, critter index, whichever. That way, if it's false, we're appending false. If it's true, we're appending true. And finally, actually, let's move these comments inside of the if statement to clarify what's happening here. So elif living neighbor count, neighbor living count, is greater than 3, New World Order, sub -1, dot append false. And now we want to be able to see what is happening with our world. We want to know if this logic here is correct, because I wouldn't be surprised if I screw something up. So we're going to start with a print world. And the bottom here, now that we've rearranged our world, we're going to set, or we've created our new world rather, we're going to assign New World Order to world. So world equals new world order. And why is it grumpy about the variable world here? Unindented amount does not match previous indent. Oh. Oh, yeah. There we go. So just because I'm fighting with 2 spaces versus 4 spaces currently, let's sanity check with black. Make sure everything looks good. All right, and we're going to print the world every time, and we're reassigning our world, but we won't really be able to see a clear progression of what's happening until 2 things happen. We need to slow down the execution so that our slow, dumb human eyes can see stuff. And then also, we want everything to be positioned in the same spots for every iteration of this infinite loop. So let's do 2 things. Do from time import sleep so that we can slow down the execution a little bit. And let's do it at the very end here. We'll do a sleep, I don't know, 0.1, so 1/10 of a second. And another thing that we want to do is we want to clear the screen every iteration of this loop so that every single time we print the world, everything ends up in the same position it was from the previous run. It's going to make the screen flicker a little bit, but we'll be working through that in a later iteration of our code here. Off the top of my head, I don't remember how to clear the screen in Python, so let's look it up. You know what? Let's ask Copilot. This is exactly what Copilot wants, likes, can do. How do I clear the terminal in Python? All right, for Windows, for Mac and Windows. Okay, this is not really the way I want to do it, but that's fine. Like I said, we'll be doing this in a better way later on. So right before every print, we're going to clear the screen. We're going to import OS. All right, and let's see how we did here. Let's reformat. And main. All right, something went more or less right. Let's try increasing our density. We said less than or equal to 5. So let's change that to 15% density and see if that looks any different. It's not changing. So what did I miss? I think, yes, we need to move this inside of the loop. There we go. That looks great. And to my surprise, the flickering actually isn't that bad. All right, we've reached, there's probably a technical term for this. I call it equilibrium. Everything is happy and hunky-dory. So ultimately, this is version 1. Between coding and recording the video, this whole process took me about an hour. I think I am going to split this series up into 3 videos. So episode 1, 2, and 3, parts 1, 2, and 3. I'll figure that out later. But consider this a 3-part series, this being the first part, and I'll see you all in the next one. I hate it when people say that. I won't see you. You'll see me. You'll see me in the next one. All right, thanks.